This is Lab 5 on magnetic braking and Faraday's Law. This lab examines the impact of Faraday's Law by observing a falling magnet. The magnet acts as an external field, and the inside of the aluminum tube is the current. And we need to find the force on the magnet by the tube. This force breaks the magnet, or slows it down while it's in the tube. Some important principles and concepts for this lab are Faraday's Law, dipole fields, magnetic flux, and induced currents. For this experiment, I recorded 6 attempts of me dropping a magnet into a tube and determining the average time the magnet was in the tube. After recording my attempts, I took the tube length and the radius and the thickness of the foil for my coding model. And you can see the values that I labeled right under it. And one important thing I want to note was that a non-ferrous aluminum tube was used. And the reason why a non-ferrous tube was used compared to a ferrous one is that a ferrous tube would have more magnetic properties, and it would probably mess up the field reading during the time, or the magnet might get stuck to the walls of the tube. For the coding model, the main thing I really wanted to focus on was one, the calculation of the deflux over time analytic model, as well as the while loop that was used in order to calculate the force on the ring over time, or the magnetic force in the ring over time. So some model observations that I made were first that the simulation for my magnetic dipole reading was a lot longer than the actual experiment, with my normal experiment being 2.6 seconds versus the computer model being about 32.2 seconds. And the other thing was that the graph had a nonlinear trend that matched the idea of magnetic braking, where when I first dropped it in the tube, it shot up in speed, but once it was inside the tube, it stayed at a constant speed and not slowing down or speeding up at all. But then once it exited the tube, it dropped down back to 0. So to finish off with some important observations and questions, first was what would happen if I changed the resistivity of the tube to about 0? And resistivity is a material property that's dependent on resistance, length, and area. So the equivalent of having resistivity equal to about 0 would almost be like saying that your resistance is about 0, which in the formula for current, that would mean that the current is almost infinite, since current depends on resistivity and resistivity depends on resistance. So what if holes were cut into the tube? You can kind of think of it kind of like how for when you're calculating the magnetic field, it has to be completely enclosed in order to have a magnetic field reading. So when the magnet passes through those holes, the magnet speed would increase because it's no longer being covered up and there's nothing that's helping with the braking. And then it decreases when it's fully enclosed by the aluminum in the tube again. And the last question is, why is the simulation so much longer than the actual experiment? And I personally believe that the time is impacted by a magnetic dipole moment and a magnetic force. And the magnetic force is larger in the model because realistically, or with the formula, as the dipole moment decreases, the magnetic force is also going to get weaker. Which, when the magnetic force gets weaker, that means that there's probably a larger speed in the end.